Hello, this video presents our new path planning framework which integrates machine learning models in a decoupled way to leverage previous experience. A small change in the workspace can have a huge effect on the configuration space. Therefore, it is difficult to use previously solved problems to help solve new ones. Recently, learning-based planners are becoming popular. Machine learning models could be used to generate a path and solve planning problems. However, they usually do not have any guarantees on the success rate. Worse, trying to correct the predicted path is also not guaranteed to succeed. Our framework combines machine learning with path planning in a totally decoupled way. The machine learning model takes the problem as input and outputs an initial trajectory that will be used by the ITIRRT planner to initialize its data structure. The planner is probabilistically complete and can leverage the data learned by the machine learning model. Because our framework completely decouples the machine learning model from our planner, the model can be freely swapped at any time, including runtime. Our planner is called ITIRRT for Independent Tree Initialization RRT. At the start, the planner takes a predicted path as input and uses collision checking to break it into multiple trees. In this situation, we initialize both the start tree and the goal tree, but we also created two independent trees. ITIRRT process is almost similar to RRT Connect, with an added step where we try to connect the currently processed tree to the closest independent tree. When an independent tree is connected to the start tree or the goal tree, it stops being independent. It is important to note that our planner does not correct the prediction path, which means that it does not need to use all the independent trees. This makes it robust to a bad prediction. We perform experiments on two simulated environments and one small physical robot. We chose them to highlight the benefits of leveraging experience to quickly solve challenging problems. The first simulated environment is a 6 degrees of freedom planar robot having to move from one side to another while avoiding randomly placed box obstacles. The second environment represents a typical industry problem where a 6 degrees of freedom industrial robot had to move from a bin to a shelf. It is a challenging problem for most path planners due to the narrow space in the shelf. Finally, we perform experiments on a small physical robot named MyCobot. The robot had to go from one bin to another while avoiding the hand of the operator. The hand was modeled as a cube, and its position was detected using OpenCV Aluco marker immediately prior to the execution of the path planning. We compared ITIRRT to RRT Connect on the previous environments. We combine ITIRRT with three machine learning models: a multi-layer perceptron, a long short-term memory, and a conditional variational autoencoder. The results show that leveraging experience brings a large speedup of the computation time. We also combine ITIRRT with a randomly initialized machine learning model to illustrate the effect of a bad quality model. We observe that, in this situation, our planner was performing on par with RRT Connect. We presented a path planning framework leveraging previous experience using machine learning models. The machine learning part and the path planning part are completely decoupled, allowing to keep convergence guarantees. It also makes it possible to change the model to adapt to different situations at any time, including runtime. Our ITIRRT planner can use any predicted path to initialize its data structure. The paths are not required to be generated by a model, but could be obtained from anywhere, such as a dataset. We implemented our framework as a planner in the OMPL library. The source code can be found on GitHub at the following link. Thank you for listening.